Okay, so here we are looking at training module 7, and in this we're going to be looking at the effect of an aftercooler on gas compression two-stage. So to start off, as usual, we're going to create the sources and the sinks. So we click up here, our source here is nitrogen at 25 degrees and 0 bar gauge, so I'm going to call that 0 bar gauge nitrogen, and we also want to create our fluid sink. This will be a 16 bar gauge sink. So I'll call it 16 bar gauge sink. Alright, and now we want to create the line itself. So we're going to be using a standard connection size to start off of DN200 schedule 40 pipe. Heading north, and this is our source here, which is the 0 bar gauge nitrogen. I'm going to elevate it by 2 meters just because to keep it off the ground. So to start off, we'll add in a pipe length, and then we've got a compressor. This compressor is going to be the first one. It's going to have DN200 schedule 40 input and output, and we're going to leave our default compression curve and motor efficiencies. The only difference I'm going to change, so I'm going to make it 304 stainless as with all of our fittings. So you can see here, this is the output of this is facing upwards as we want, and we're now going to put a cone section on to resize it. So the input will be the DN200 schedule 40, and we're going to resize it down to DN100 schedule 40. And we're going to make it 15 centimeters long. And again, the fittings will make of stainless. And you can see here this pipe has come up red because it's not going to fit because of the resizing. It's not within the tolerances. So we've got to define a new pipe here, which will be of the smaller size. We've now got a bend. This will be a bend to the north. We'll add another meter of pipe, and we want to put in our first heat exchanger. This will be defined as follows: multiple tube rows with a tube sheet connection, circular tube bundle, triangular tube pitch, and domed end cap. The diameter of 1 meter, a tube length of 5 meters, and everything else we leave as it is, except for we'll make it of stainless. So there we go, we've got that. And we want to bring the pipe around to the front now. You can see that in the diagram there. So we'll add in a turn left, a meter of pipe, another turn left, and I'll make this 5 meters long to bring it back. And we now want to turn down, meter of pipe, and then we can put in our globe valve here to control the flow. So we'll define our globe valve with the default valve curve, but we're going to start it off 90% open. And again, we'll make this out of stainless. You can see that's the valve curve, it all looks correct. So you add that in, and another meter of pipe. There it is. You can see this is a bit long here. I know that's right, I've still got a bit of space above the ground, but I'm still going to resize these a little bit because it's down below the source. I want these to be up a little bit higher, so I'm actually going to make them 1/2 meter each. Okay, we're now going to turn to the west and add in a pipe length and our second compressor here. So we'll define our second compressor with the default compressor curve made of stainless. And we can see here that the output is off to the side here. As we're recreating that diagram, you can see at the bottom right, we're going to rotate this by 270 degrees to bring that up to the top. There we go. And to start off, we don't have a second, we don't have the aftercooler. So we're just going to add in a meter of pipe, turn to the north, another meter of pipe, and our 16 bar gauge sink. The last thing we need is the water cooling on that heat exchanger. So you can click to add it and then edit it as follows. We want it to be exposed to the all of the pipes with a box temperature of 30 degrees, 4 bar gauge pressure, and 3 meters per second velocity. So this is all correct. We can now solve this system by clicking the play button, and we want to have a look at the temperatures. To start off, we'll note there's a heat loss of 383 kilowatts, and we can click on the fluid temperature on the left hand side here to see, as we expect, it heats up through each of these compressors and it cools down as it's going through the intercooler. And we can look at the results graph if we want some numbers to sort of back this up. By dragging this around, we can see that at the output it's about 326 degrees Celsius. And if we tick the move 3D axis option, we can see exactly where that's occurring, and it's at the end here. It's between 330 and 325 degrees. So now we can have a look at the effect of another intercooler. So to do this, we can copy it from here and paste it downstream of that pipe length, and there it is. You can see it didn't copy with the water, and that's right, because we're going to start off just by seeing what effect we have when we don't water cool this aftercooler. So by solving this, we can look that the heat loss is 551 kilowatts, which is higher than the 303 that we got earlier, so that's good. We're losing a little bit more heat, not a huge amount more, but we can look at the fluid temperature. Again, you can see that that cools a little bit down to this yellow region here. And looking at the results graph, we can see that after the second one, it cools down to about 234 degrees. So that's down from 326 originally. However, now we can try it with the water cooling. So we click to add that water cooling jacket, and we're going to leave these as default. That's the same as we had before. We can click play to solve it. Alright, now we find there's a heat loss of 869 kilowatts, which compared to the 303 to start off is a huge amount more. We can have a look at the fluid temperature and see that it gets down to this blue again, and we can look at the results graph to find out what that corresponds to. If we drag it to the end here, we find it's 56.3 degrees. So very different to the initial 326 without the aftercooler, and much better than the 234 that we were getting before. So that's how we can have a look at the effect.